Hello. In the previous video clip, the quick start showed us the different possibilities of showing points and actions. In the present version of the program, we added possibilities to open several exercises on the same computer, and we have added some actions to show the bypass factor and the discharge conditions of a coil, but also to draw a line representing a certain sensible heat ratio. In this clip, we will highlight them through two practical exercises. First, we will see that for this sky-air combination here, connection to the RZQ200, we will see the properties of the indoor unit that is connected to that system, which is the FDQ200B, which you see here, nominal air volume and airflow rate of 69 cubic meters per minute, so that's about 1150 liters per second. And we will see for the outer unit, that is of course determined by the temperature of 35 ambient, at these nominal conditions of 1927, we will find a total capacity of 20 kilowatts and a sensible capacity of 15.6. So this is what we get. What do you want to know? Well, we want to know the air off, or the discharge condition of the air of that indoor unit. We want to know the coil bypass factor, and we want to see how much moisture has been removed from that room in 1 hour time. So let's do that exercise. So we click on New, and we will set the first condition, the air on condition. So P1 we override as air on. Condition to be 27 degrees dry bulb, and the nominal condition are expressed 27 and also wet bulb of 19, with an air volume of 1150 liters per second. Okay, I can click on Add to see this on the diagram, and of course what I can do is zoom in. You know that with the wheel action on the mouse, we can using the control key we can zoom in. Using the shift key you go left and right, and simply with the wheel you go up and down. But so I have the air on condition just here, and I can visualize this better by simply clicking on show point actions, where I get these two dotted lines, but they will come in handy later on, as you'll see. Okay, this first point has been set. Another action that we can do is to show the sensible heat factor line. So sensible heat factor line, what do we need that therefore? Well, you know that capacity wise we had 20 kilowatt cooling capacity total and 15 sensible, so the relation of this will give us a sensible heat factor of 78%. So 78%, and clicking on this color here to change for sensible heat ratio line. Okay, what we see here, add, this is the line of the relation between the total and the sensible heat. Good. Another thing that I can do now is to show the, because one of the questions that we had was to show the bypass, the coil bypass factor, okay, and the air off and discharge condition. So I can go to the bypass factor right away, go to bypass, and ask this for a sensible heat factor of 78 and a capacity of 20 kilowatt. Give it, let's say, this color here, yeah, and if I add, this is what I get here on the screen, and you see that my discharge condition, or my discharge temperature, will be 16 degrees. I can, by the way, rename this condition here by editing, and now I can modify this point PP2 into discharge, yeah, and accept this. Yeah, so this is my discharge condition. If I highlight this discharge condition, you see all the psychrometric data here, and it's also one of the point names that we have in there. You see the bypass factor is indicated in 27%. Yeah. So this is what was asked. What was an additional question is that we need to see the condensate removal rate per hour. So if we want to see that, well, we have to remember that the density setting normally in the exercise, if you see the preference, the diagrams you have here, the standard value that you use, that question mark will give you more information about that. So standard value will always be used in the program. We will just use this density of 1.2 cubic meters per kilogram to multiply this by the air volume, the 1150 liters per second. So setting the units right, this will give us 1.38 kilograms per second mass flow rate, and what we will need next to that mass flow rate now is also to know the difference in absolute humidity between the air on and the discharge condition, so that 4.8 grams we can multiply by this 1.38, and this will give us 6.6 grams per second, or multiplying this with 3000 size, multiplying this with 3600 will give us 23.76 liters of moisture or water that will be collected from that coil. So quite a bit, of course. In the second exercise, we will not consider what happens with the unit, but we will consider what's happening in a room. A room with a certain load, a load of 20 kilowatt latent and 80 kilowatt of sensible. And we see, of course, the relation between this will be a sensible heat ratio of 0.8. Okay, there will be 70% in that room, and they all need some fresh air. They will need about 12 liters per second fresh air, so that will be about 840 liters per second. The state point of the room will be 22 degrees, 50% relative humidity. The ambient condition 32.55, and the minimum of temperature that is asked in that room would be 12 degrees dry bulb. Okay, what we need to find is the mixed air condition of the entering air at the cooling coil, the required air volume, the required air off condition. We know already 12 degrees, but yes, but there is much more to be said about a certain condition of air than only the temperature. We will want to know the required cooling capacity that we will need to do with the air that will be circulating in over that coil, and we want to know the coil bypass factor. Okay, so let's click on New. So we clicked on New, and the first thing that we will have to do is actually to set the state point for the room that we will abbreviate as the letter R, with the letter R. So the letter R over here, and we see that we need to set this to 22 and relative humidity of 50. Okay, I add this, and we also have to set the ambient condition, which I will put here as AMB, and that was 32, and the relative humidity of 55. And I add this point also in my diagram. So let's look at closer. This is what it looks like here now. Okay, next thing that I will have to do is to check how much air we will have to produce in this installation to overcome the load that we had. So that load that we had again consists of 80 kilowatt sensible and 20 kilowatt latent, so with a sensible heat ratio of 80%. Okay, so how to do that? Well, we see that we have to account for the required amount of air, and that would be 80 kilowatts divided by the density, and again divided by the temperature difference between the room temperature and, remember, the minimum air off temperature that was decided to be 12 degrees centigrade. Yeah? Later on we will call that point S. Good. So that amount of air that will be required to cover that load will be 6,667 liters per second. The amount of fresh air will be 12 liters per second per person, 70 persons, is 840 liters per second. The amount of recirculated air will be to deduct that fresh air from the total amount that needs to cover the load, so that will be the amount of recirculated air. Yeah? So let's put both the fresh air and the circulated air amount quantities in. I have to set the ambient air amount, so I edit it, it's still highlighted, I edit it, and I change this to 840 liters per second, and I accept. Whereas the amount of recirculated air, I select that point, I edit that point, and I set the amount of recirculated air to what we set to be the difference between 6,667 and 840, being 5,827 liters per second. And I accept this as well. What I want to know now is to apply that sensible heat ratio, so that sensible heat ratio of 80%. So what I'll do is to take the action. First of all, I can show the point on my diagram, the point R, but then I can add another action where I want to see that sensible heat factor of 80%. I choose another color for that. Here it is, and I add this. Okay, so what I am interested in now is to actually know the point of my discharge temperature. So on this line of sensible heat factor, the capacity of the unit representing the kind of capacity of the unit that we will need, we see the temperature of 12 degrees being the lowest temperature. Let me zoom in again. And if I hover on my diagram and I go to the point of 12 degrees on that line, I see in the point data, that will appear here, I see in the point data that I can specify a new condition with a dry bulb of 12 degrees and a wet bulb of 10.4 degrees. So that's what I'm about to set now. A new point that I will call S, and here I put this in 12 degrees dry bulb and a wet bulb temperature of 10.4. Now the amount of air that I will need there will be the 6,667 liters per second, and I add this. This will be the point S. I can visualize it better by again choosing the command show point. Where is it? Show point, and show the point S, and select a color red, for instance, for that. Okay, and I add. This is my point S. So I zoom down to see again that ambient air condition here. Now, because I want to know what would be the condition of that mix. You know that R was set to be the recirculated air and the 840, so I can choose command mix air and mix the air between R and ambient and show this with a color, okay, another color, let's say green, and okay. So I can add this and see that my mixed air condition, by the way, I can rename that. My mixed air condition would be not the point PP2, but I call it mix over here, and accept. So this is my mixed air condition. Now, interesting to see would be the amount of capacity that I will need to go from that mix point to the supply point in that room. So I want to know the cooling capacity to cool this mix down to the supply. I have the action cooling, and in the action cooling I want to go from the mix point and to go to the point S. So I add this. Let me give me an orange color. But what we will see now is that when I add, I get the auxiliary lines here with an intermediate point. This means that, considering this action, I will need a total of 133.05 kilowatt, out of which 91.53 is sensible and 41.52 is latent. Okay, good, interesting information that I have here, but I want to keep my drawing as simple as possible, so therefore I'm not interested in these intermediate this intermediate point and these lines. So I can edit this action. It's still highlighted here in blue. I can edit this action and not showing the intermediate lines and accept this. So this is the capacity that I would need to go from point M to point from the mix to the supply. So looking again to what was requested, we need to find the mixed air condition entering the coil. We found it in the point M, the mix. The required air volume we calculated right at the start. It was 6,667 liters per second. The required air off condition, again it was the minimum of 12 degrees, but you see here, if you click on the S, you see that we specified it with two conditions, but clicking on that point or positioning on that point, you see all the point data that appear here, so much more than simply the dry bulb and wet bulb condition. You get more information there. Good. Additionally, we require the cooling capacity. Actually, this is from mix to S, and we saw that this is composed out of sensible and latent, and we kept it simple, so we did not want to see the intermediate lines. Okay, good. The next question, or the last question, would be to give us the coil bypass factor. So to find this coil bypass factor, we have a action for that, and that will be somewhere here, the bypass factor. Okay, let me choose another color to show this. Okay, and then I will need the bypass factor from the mix point, and it will be with a sensible heat factor that we obtained here in that cooling action of 69%. Voila, and I can add this point. So here, this is the bypass factor that we are obtaining here. We see that we will have a bypass factor of 30.8%. Okay, we have seen that okay, our capacity here, our room load, was actually 100 kilowatt, and we see that in total now we will need 133 kilowatts. So considerably bigger capacity due to that fresh air. So needless to say that we can reduce the load again if we would have the means of let's say installing a heat exchanger. Or that heat reclaim ventilation device could have a total heat exchanger like in our VAMs, or could be another means of cross flow where you would actually exchange the exhaust air and the fresh air, and thus have a preconditioning of that fresh air in your room and having less load in your room. With this we finalize this exercise, but not without thanking Kamal Bhattacharya from Daikin UK for his active contribution, and I thank you for your attention. With this we wish you a Merry Christmas and a Happy New Year. Bye for now.